Hi everyone, welcome back to another video. So in case you're wondering, I've got some lemons on my desk. We're going to have a go at experiment 5, although I don't have that much confidence in it. Apparently we're going to be building some sort of a battery using lemons, so it should be an interesting one. I'm not actually sure if I have the right equipment for this, but let's just give it a go. And I'm actually expecting this video to be a failure, but you never know. Let's give it a go anyway. So just jump straight in. Oh, and I should mention that obviously we're going through the Make Electronics Learning Through Discovery book, which is a fantastic book for anyone who wants to learn how to do electronics. I've gone through the book myself a fair bit and learned quite a lot from doing it. I didn't actually do this experiment though, because I figured who wants to be cutting up lemons on my desk? But I'm going to do it for you guys, so let's get into it. Alright, long ago, before the web existed, kids were so horribly deprived they tried to amuse themselves with kitchen table experiments such as making a battery by pushing a nail and a penny into a lemon. Hard to believe, but true. Now that modern LEDs will emit light when just a few milliamps flow through them, the old lemon battery experiment is more interesting. If you've ever tried it, the time is right. Or if you've never tried it, the time is right. Okay. Alright, sure. Okay, so what we need for this video is, as you can see here, I got 3 lemons because I'm not entirely sure how this is going to work, but apparently you only need 2 lemons for the actual experiment. We need some copper coins. So I'm in the UK. I don't know if my coins are copper plated or not. No clue. But yeah, apparently they need to be fairly shiny as well. So I've got one dull one here and then 2 decently shiny ones. That one's a bit oxidized, but this one's quite new. We need 1-inch zinc plated steel brackets. I'm showing you this steel bracket. I mean, I don't even know if it's steel, to be honest with you, but it's a bracket. I don't know if this is the right thing to use or not. I don't know if this is zinc plated, who knows, but we need 4 of them and I've only got 3 of them. So yeah, I don't know if this is, again, we'll see how it goes. We also need 4 alligator clip leads. So we've got 1 black one, 1 red one, and then 2 green leads, like so. We need a multimeter, and finally a low current LED. I actually don't know if this is a low current LED. I don't even know what that really means. He actually mentions here that C light emitting diodes for a reminder of the difference between generic and low current LEDs. But I'm just going to use the standard or whatever LED I've got and see if it works. Again, like I said, I'm just not expecting this experiment to work, so I'm just going with whatever. All right, let's get into it. So a battery is an electrochemical device, meaning that chemical reactions create electricity. Naturally, this only works if you have the right chemicals working for you, and the ones I'm going to use are copper, zinc, and lemon juice. The juice should be no problem. Lemons are cheap, or you can buy one of those little yellow plastic squeeze bottles of concentrated juice. Either will work. Pennies are not made out of copper anymore, but they're still plated with a thin layer of copper, which is good enough. Just make sure that your pennies are new and bright. So I've got 1 bright one, 1 medium, and one definitely a bit dead. If the copper has oxidized, it will be dull brown and experiment won't work as well. So yeah. Zinc is a bit more of a problem. What you need is a metal part that is galvanized, meaning it is coated in zinc to prevent rust. Small galvanized steel brackets should be available at your local hardware store and they don't cost much. Brackets that measure about 1 inch along each side will be fine. Okay, so cut a lemon in half and push a penny into it as close as possible to the penny, but not touching it. Pushing your galvanized bracket. Now set your multimeter so that it can measure up to 2 volts DC and hold 1 probe against the penny while you hold the other probe against the bracket. You should find that your meter detects between 0.8 and 1 volt. That's amazing. Okay, let's give this a go. Because if this doesn't work at this point, then, obviously the experiment's not going to work. So, all right, let's cut up a lemon. So another thing I'm concerned about is the lemons I've got are not the best lemons. Basically, they were. I bought them about 4 days ago, but I just haven't had the time to do the experiment. I've been busy with uni work, so I've been trying to protect them and preserve them. But yeah, I don't know. I don't know if these are going to be right. So this one seems like it's been a bit bruised. This one seems a bit better, so I'm going to go with this one. Try this one. Okay, so we're supposed to cut the lemon in half and push a penny into it. So, not quite. I mean, it's alright. It's not off or anything, but okay. So we got half a lemon. All right, now they want me to push the penny and a galvanized bracket into it. So we'll go with the penny first. So it needs to be in obviously the juicy part, right? So that into there. I've gone with my brightest penny that I have. I mean, it's not really going in. Oh dear. Okay. I can't really see this going in as well, but okay. All right. So that's in, and I think they're not touching, but I think it's gonna fall down. So I think there's a decent enough gap between them. Let's go on our multimeter now and set it to 2 volts DC. Is over here. Oh dear, knocked it. Oh, we're losing lemon juice, people. Okay, so we are expecting. Oh my gosh, I cannot wait until we're just doing projects and circuits on a breadboard. Just all of this alligator clip stuff is all just too finicky. Okay, so we're expecting a voltage of 0.8 to 1 volt. Okay, come on, please work. Look at that. Oh, we had it there briefly. It's all over the place right now. Wait, hang on. I'm like I'm moving the penny. It's not really in there properly. But okay. So the bracket is in there fine. So let's hold that against that and then just touch the penny. So it's not stabilizing, but you can see it's going from 0.1, 0.2 up to 0.9 volts. That's amazing. I'm actually buzzing. That's great. I mean, there's no stable voltage. Maybe I wonder if this is affecting things. Gonna fall down. All right, so now I've got the multimeter holding up the bracket because I'm a bit concerned that maybe like there's a voltage issue because the bracket's so large. Because I was like, kind of extending it, wasn't I? So let's try again. Again, it's still just like fluctuating like crazy. Kind of stops at 0.9 volts. All right, let me try and adjust it a bit more. Okay, I'm just gonna try and maybe push this in like this. It's actually really hard to do. Okay. Okay, I think they're not touching like that. I'm getting covered in lemon juice. All right. No. It was a bit more stable, but then no. Okay, well, I'm gonna take this as a success and just hopefully try and continue with the experiment. But I had a feeling that this was gonna be a difficult one. So what I'm thinking is, if my whole experiment goes like that, where it's just fluctuating like crazy, more than likely, maybe the LED, if I do get it to work, it might just turn on and off, on and off. Which may or may not be a good thing. We'll see. Oh man, I feel like I should get changed for this experiment. I'm ruining. Getting lemon on my nice trousers. Okay. So to power a typical LED, you need more voltage. How can you get it? By putting batteries in series. In other words, more lemons. You'll use test leads to link the batteries as shown in figure 1.64. So this is the one that we're going for, right? All right, I've got it. I understand this now. So the penny and the copper penny and the zinc plate are creating a voltage drop between them with the lemon juice. And then now we're going to put them in series to build up. Technically, even though, I've got a fluctuating crazy battery over here, if I just put loads of them in series, I should fluctuate, I don't know, like between whatever. Let's say if we got one lemon 0.2 to 0.9 volts, that means that 2 should be 0.4 to 1.8 and so on and so forth. So this could actually work, although I actually don't have enough plates and pennies. Especially this is my best penny, so more than likely my other pennies are probably going to perform a lot worse. Oh dear. Okay, so notice that each lead connects a bracket to a penny. Do not connect pennies to pennies or brackets to brackets. If you set things up carefully, keeping the pennies and brackets close to each other, but making sure they don't actually touch each other, you should be able to illuminate your LED with 3 lemon juice batteries in series. Another option is to use little parts box divided into small sections as shown in figure 1.65. When everything's nicely aligned, squeeze some concentrated lemon juice, vinegar, or grape juice may also work. So let's see this one. Oh, okay, this is much easier. So he's literally, okay, connected a penny to the box. I could possibly do that. That seems like that would be easier. Let's give this a go anyways. This looks more fun, right? Although I'm not enjoying getting covered in lemon juice. All right, so that's our first lemon battery. Let's make our second one. All right, so push this in here. Trying to make sure that I don't, oh dear, just tipped it all out. Trying to make sure I don't pierce the bottom. Blech, ugh, I just licked my fingers. That is gross. Okay, how am I gonna get this penny in here? I think that might be touching. All right, so that's our second battery, I think, done. I mean, we can probably test it to see if we've made it correctly. Look at that, we're getting the same sort of fluctuation. It's not going as high, but it wasn't going as low either, so that's quite good. Okay, another lemon. Don't know what this lemon is going to look like inside. Would I recommend trying this experiment at home? Depends if you like cleaning. I'm currently covered in lemon, which I don't like to get messy. All right. Okay, so this is our final battery because I don't have any more copper coins. Okay, let's stick this first. This one's actually cut better than those. Can't get it in. Okay. So I'm expecting this battery to perform the worst because obviously this is just a brown penny. Not shiny at all, so see what we got. Ah, it's good. That's getting over 1 volt. Look at that. The rubbish penny apparently is the worst. Or is the best. Okay, so now we need to get our 3 batteries. Yeah. Okay, so we've lined them up. Now we need to connect them in series. So we're going to the plate, and then this one's going to penny. Okay, and then again plate to penny. Kind of just moved those. Okay, so plate, penny. Oh dear. Okay, so now so the battery's all connected now, and then now we just need an LED across them. So the longer lead of our LED. Okay, that, and then this one going to the penny. Oh man, so difficult to do. And then negative. Oh dear. Okay, and then going to our plate. If it's gonna work, if I touch it now, it should turn on. Oh, look at that! It worked. It turned on. Look at that. That is brilliant. Wow, look at that. Look at that. That's amazing. Wait, let me try and turn off some lights. As I've like moved this plate over, so oh dear. Okay. All right, 1 second. It's brightly dim because I think this isn't a low current LED, but still, 1 second. Let's turn some lights off. I'm absolutely blown away. So as I close the distance between these two here, because okay, this battery is the worst one. It's like stuff's all over the place. But as I close the distance, see it turning on. Look at that. That is crazy. That is absolutely crazy. Yeah. Oh man, this is brilliant. This is definitely an experiment to do with the kids. I'm amazed. I had zero confidence that this was gonna work. What a brilliant experiment. And you see what I mean? Like this is a brilliant book. Really, really, really good book. So as I close the distance between these two, the LED goes brighter. So probably if I adjusted all the other batteries and did them properly, this would be a lot better. You see it there flickering. Amazing. Absolutely amazing. So I've redone this battery, the one over here, and then now when I touch it, get a nice bright LED. You can see that obviously the voltage is fluctuating as we saw from our multimeter, and that's causing the LED to dip. It's dimming in and out. That's amazing. Look at that. I cannot believe that. That's crazy. Okay, so that's the experiment done. I think let's just have a quick glide through the rest of the chapter, just see if there's anything worthwhile mentioning. Because I've decided to have 4 cells in my juice battery because the LED pulls the voltage down somewhat, and the battery is not capable of delivering enough current to damage the LED. Yeah, definitely. If I was to use more and more, it would be a lot better. So to understand why the lemon battery works, you have to start with some basic information about atoms. Each atom consists of a nucleus at the center containing particles called protons. Blah, blah, blah. Okay, breaking up the nucleus of an atom requires a lot of energy and can also liberate a lot of energy. But persuading a couple of electrons to leave an atom or join an atom can take very little energy. For instance, when zinc reacts chemically with an acid, so zinc is our plates, reacts chemically with an acid, i.e. the lemon juice, right? This can liberate electrons. Interesting. The reaction soon stops if the plated part isn't connected with anything, as electrons accumulate with nowhere to go. Got it. That's what copper's there for, because obviously copper is a conductor of electricity. Interesting. Nice. That makes sense. So it's because the zinc is reacting with the acid, which is liberating electrons causing electrons to leave from the zinc. Got it. The reaction seems okay, so they have mutual force of repulsion. You can imagine a crowd of hostile people. Here they're talking about electrons, that's fine. Now consider what happens when a wire connects the zinc electrode, which has a surplus of electrons, to another electrode made from different material, such as copper, which contains holes for the electrons to occupy. The electrons can pass through the wire very easily by jumping from one atom to the next. As soon as we open up this pathway, mutual repulsion makes the electrons try to escape from each other to their new home as quickly as possible. This is how electric current is created. Brilliant. That is absolutely fantastic. Now that the population of electrons on the zinc electrode has been reduced, the zinc acid reaction can continue, replacing the missing electrons with new ones, which promptly imitate their predecessors and try to get away from each other by running down the wire. They move with such a force we can divert them through an LED, and they will liberate some of their energy by making it light up. Brilliant. So here he's talking about flow of electrons, which can have a negative charge. So he's going to talk about Benjamin Franklin and how he had a choice between positive and negative, and he got it the wrong way around. But that doesn't make a difference. Nice history, so have a read through that. Here he's just talking about components being labeled from positive to negative, even though that's not the way that it actually works, which is fine. Basic measurements. I'm going to backtrack now to the kinds of definitions you would normally find at the beginning of electronics texts. Amps, coulombs. Okay, that's fine. We can skip all that. It's talking about watts and joules. Practically speaking, for practical purposes, I think an intuitive understanding of electricity can be more useful than the theory. I like to go back to the water analogies. Yes, you know what? Actually, last year when I was in my first year of electrical engineering, I was reading his water analogies, and they were absolutely fantastic. Proper game changers for me. So I definitely highly suggest if you're struggling with just understanding the flow of electricity, the water analogies are fantastic. Even though obviously proper electrical engineers and physicists would tell you that that's not how it actually works, but whatever, doesn't matter. Okay, so this is just his nice water analogy of how a battery works. It's interesting. Here he talks about putting batteries in series. And that's it. The hardware that you immersed in lemons or lemon juice may be discolored, but it is reusable. Bearing in mind that some zinc ions have been deposited in the lemons, eating them. I was gonna say that I'm still gonna use these lemons, but I think he's made a good point here that since there's now zinc inside my lemons, I'm not gonna eat it. Although I didn't use a lemon and a half, so I think I can still put those lemons on my pancakes. Yeah, that was cool. All right, so that's the end of chapter 1, which is basically the beginning part of this book. The next part of this book, experiments 6 through to 11, they get really good. You know, now we're talking about actually breadboard stuff, and he goes into some of the tools that you use. So we'll cover those in the next video. If you're enjoying these videos, leave a like. Let me know what else you'd like to see in the comments. And yeah, I mean, if I was you guys, I'd try this at home as well. It was a lot of fun. There's something special about making something yourself. Like it's a brilliant feeling. Like I'm buzzing right now. I was not looking forward to this video at all, and now after doing that, that was a lot of fun. And I like the idea that one day I'm going to sit down with my kids when they're old enough to be able to understand a bit more about what's going on and do this experiment. You know, so I look forward to that a lot. All right, guys, thanks for watching. I'll see you guys in the next one.